Thank you all for coming here to my presentation. I also would like to thank the committee that read my thesis and evaluated all the thesis, and the organizer for inviting me for presenting my PhD. So I did my PhD in the Federal University of ABC. This university, if you don't know, it's here in the metropolitan region of São Paulo, in the ABC region. That's why it's called ABC. And it's a new university. It was built in 2006. And my advisor was Cecilia Quirente. So I'll talk about my thesis, which I titled Black Hole Spectroscopy, Prospect for Testing the Nature of Black Holes with Gravitational Waves Observations. So just to give a brief overview of what gravitational waves are, I know there was already 2 talks about it, and there will be tomorrow more talks about it, so I'll be brief. So it's old news that gravitational waves were detected in 2015 by the LIGO collaboration. And for this, they awarded a Nobel Prize. And here in this plot, I'm showing the first detection. So it's a detection of a binary black hole merger. We can clearly see here the power spectrum. So it was a very strong detection. So these are for the 2 detectors, 2 LIGO detectors. And with these new observations that are done by these detectors, we can analyze a lot of new things because we're now detecting gravitational wave strain. So the direct information from the source, and this opens a new field in physics, which we call gravitational wave astronomy. Just a brief overview about the detectors that are operating today. We have 4 detectors operating. 2 are the LIGO detectors, so 1 in the USA. Then we have the Italian detector, which is Virgo, and the Japanese detector, Kagra. There's also a German detector, GO600, but this detector is not sensitive enough to detect gravitational waves. So, and the detections of gravitational waves are divided in observing runs, because in each observing runs, the detectors stop detecting, and they develop better technology, so they become more sensitive. They can detect more things. So in the first observation run, there's only the 2 LIGO detectors. Then Virgo joined the collaboration in the second run, and Kagra recently joined in the third one. So there's a huge gap here. That's because of the COVID pandemic. But the 4th run should start next year. And they also plan for the 5th observation run. There's also a plan to build another LIGO detector in India. So there's a plan, but it's not built already. Just a brief overview about the detections that were made. All of the detections come from a compact binary system. Most of them are binary black holes. There are 2 binary neutron stars. And there are 5 events that are compatible with binary black hole merger or neutron star and black hole merger. The neutron star can be a neutron star due to the mass of one of the objects. So we can see here in this plot in the left that for each observation run, the number of observations increase. So in the first one, we have just 3 observations. Then we had 10 in the second one. In the third one, we have a lot of observations. And we expect to have even more in the next observations. So we also see that most of detections are black hole detections. These are because they are more massive, and they are in the range of the detector sensitivity. And this is good because this is what I'm most interested in. So just to talk a little bit about the waveform emitted by a binary black hole merger. The waveform encodes the dynamical evolution of the binary. So when the 2 black holes are orbiting each other, they lose energy in the form of gravitational wave. So in this phase, we call the spiral. So the frequency of the gravitational waves increases over time. So also the amplitude increases over time. Then the 2 black holes merge into each other. And the remnant black hole emits gravitational waves, and the oscillation ceases. The part of the gravitational wave I'm mostly interested in is the ring down, which is the last part. This part is very interesting because you can approximate it with quasi-normal modes. Quasi-normal modes are solution of the black hole perturbation theory. So you have you perturb a black hole, you have a solution, and we found out from simulations that we can approximate the ring down part of the waveform with perturbation theory. So why do we call quasi-normal modes? We know very much about the normal modes. The normal modes are defined in closed systems, so we can define the boundary conditions to vanish at the boundary. So when we set these boundary conditions, this vanishing in the boundary, we get that the solution of the waveform will have a constant oscillation, so they will look like normal modes. But when we have a black hole, the black hole makes the system open, and we also have the universe, which is also open. So the system is opened in both sides of our system. So we cannot set an arbitrary position where the waveform will vanish. We cannot set a boundary. So the conditions we set is that no waveform comes outside the black hole. That's a physical condition. And no waveform is coming from infinity. So we don't keep perturbing the black hole. We want a solution of a single perturbation. And when we set these conditions, we get that the frequency of the solution, the wave solution, are complex. This means that we're going to have an exponentially damped wave. So in this solution are the quasi-normal modes. And the most important part of the quasi-normal modes are the frequencies. We can divide the frequency omega here into the oscillation frequency and the damping time. This frequency, the important thing about these frequencies is that they depend only on the properties of the black hole. So we know from the no-hair theorems that a black hole is described just by 3 numbers, the mass, the spin, and the charge. But for astrophysical black holes, we consider that the black holes are neutral, so we just have the mass and the spins. So this means that if we know the mass and the spin of the black hole, we know what are the frequencies of the quasi-normal mode frequencies of this black hole. No matter how you perturb the black hole, these frequencies will be always the same, the frequency of oscillation and the damping time. On the other hand, if you measure the frequency, you can know what are the mass and the spin of the black hole. So this quasi-normal modes, as I told you before, it was seen in simulations that the ring-down part of the binary black hole merger is well approximated by quasi-normal modes. And in the first detection already, they looked for a quasi-normal mode, and they found the dominant quasi-normal mode, which is the fundamental quadrupolar mode, the 220 mode. So how did they do that? They analyzed the waveform after the peak of amplitude, because the peak is approximately the time of the merger. It's not known. They started to analyze the waveform after this peak of amplitude, and they looked for the frequency of oscillation and damping time. So here in the x-axis is the frequency and the damping time. And they found out that 3 microseconds after the peak, the results for the frequency and damping time are compatible with the results they get when they analyze the whole waveform. So when you analyze the whole waveform, you get a final mass and spin for the black hole, you know, from simulations. And when you compare this analysis with just the ring-down analysis, you find a compatible frequency and damping time. So this is a consistent test. We detected the fundamental quasi-normal mode because we compared with the rest of the waveform. This was done also in other detections, not just the first one. But the first one was good because it was a really strong detection, and we could see the ring-down. We can't see the ring-down in all of the detections. But this kind of analysis, we say that it's a consistent test because it depends on the rest of the waveform. If we want to look just on the ring down, we can do something that it's called black hole spectroscopy. This was proposed in 2004. And we know that the quasi-normal mode's frequencies depends only on the properties of the black hole. So if we detect the dominant mode, we know we can compute the mass and the spin. But if you detect another mode, we could also compute the mass and the spin. So detecting two modes, we can check the consistency between them. So this is an independent test because it only depends on the ring down and checks if the matrix is described by the Kerr matrix. Because if it's not a black hole, a Claire black hole, this frequency, you will detect another frequencies. For example, you can detect a frequency for the 2-2 mode that looks like a Kerr black hole, then you detect another mode, and you don't find a consistency between these modes. Because the mode all the modes define the mass and the spin of the black hole. So there are two kinds of subdominant modes. The first kind are the higher harmonics, fundamental modes. So we call fundamental modes the modes that have longer lives, so they take more time to decay. And then the subdominant modes are harmonic modes, so the numbers L and M are not equals to 2. They are not the quadrupolar modes. And when you look in the simulations, the amplitude of these modes, and so here a plot is the ratio of amplitude between the harmonic mode and the dominant mode. You can see that, sorry, for the mass ratio of the binary, for low mass ratio binary, so for initial black holes with very similar masses, these modes have very small amplitudes and they increase with the mass ratio of the binary. So when there's more asymmetry in the masses of the binary. The other kind of subdominant mode are the overtones. So you have the dominant quadrupolar mode. The fundamental mode is the mode that has the longest life. And the overtones decay faster. So they have frequencies very similar to the fundamental mode, but they decay much faster. Sorry. And when you look in the simulations for the amplitude of this mode as a function of the mass ratio, you can see that they are more relevant when the mass ratio is small and less relevant when the mass ratio is high. And you can also see this is not the same scale, that when the mass ratio is high, their amplitude is very near the amplitude of the higher harmonics. Sorry. Sorry for that. So this means that the overtones are more relevant. Oh, sorry. Are more relevant when the mass ratio of the binaries are small. And this is important because most of the LIGO detections have low mass ratio. Here, it's the opposite relation. So 1 equals small mass ratio here, and 0 equals very high mass ratio. And most of the LIGO detections are compatible with equal mass ratio. So we don't expect to see much of the higher harmonics. But the overtone should be relevant. For the subdominant mode, people looked for them in the literature, so in the detections. And when they did it, they modeled the waveform with more modes, and then found out that when you add more modes, you can decrease the errors near the peak of amplitude. But this is, we call it a weak detection of a subdominant mode, because you can add more modes. So when you add one more mode, you add 4 more parameters in your model. So you are not sure if you're really detecting it or just adding more mode and get a better result. So this is not a conclusion for the detection, because the statistical evidence for this kind of detection is very small. We can really say we detected another mode. And when you look, I don't have the plot here, but when you look for the frequencies, you can't really constrain the frequencies of the subdominant mode. So before talking more about it, I have to talk about the future gravitational wave detectors. There are two kinds. The first kind are the ground-based detectors. There are three of them: the Einstein telescope, which is in Europe, the Cosmic Explorer, which is in the US, and NEMO, which is in Australia. NEMO is going to be more sensitive for neutron stars. And there are also the space-based detectors, which is LISA. It's a European project, but NASA is also in the project, and Tianqing, which is a Chinese project. So here I'm showing the plots of the noise of the detectors. So when the signal of a detection is above this curve, we can say that the signal has been detected. And we can see here that the ground-based detectors detect the high-frequency signals, and the space-based detectors detect the low-frequency signals. So as the mass of the gravitational waves is inversely proportional to the frequency, the space-based detectors will detect supermassive black holes. So even though the noise seems to be much larger than the other ones, LISA will be really sensitive because it will detect supermassive black holes. So to talk about the detectability of the modes, we propose a more conservative criteria because we want to look for statistical evidence for a second mode. The first criteria was proposed by Berti in 2006. This is a generalization of the Rayleigh Criteria. So the Rayleigh Criteria was proposed to distinguish two bright stars very near each other in the sky. So this criteria says that you detected a mode if the difference in their frequencies is larger than the maximum error uncertainty of the estimated frequency. So you have to have, it's like this plot here. So if the uncertainty is very large, you cannot distinguish the frequencies. And the same thing for the damping time. So we can see that this criteria poses different constraints for different subdominant modes, because the harmonic modes have very different frequency from the dominant mode, but their damping time are very similar. On the other hand, the overtone have very similar frequency, but very different damping time. So each of these inequality will constrain modes differently. This criteria is very restrictive. So if you can satisfy this criteria, you have a very large statistical evidence. But we can go a bit less restrictive and do model selection using Bayes factors. So we consider that, we can say that a second mode has been detected if the logarithm of the Bayes factor between a model that contains two modes, so the dominant mode plus the subdominant mode, over the model that contains just the dominant mode, is greater than 8. So this is also very conservative, but it's much less conservative than the Rayleigh criteria. And here, just a plot to check that this threshold is high enough, because we computed the Bayes factor of a signal containing just the dominant mode, and checked that none of the signals returned a Bayes factor larger than 4 here. Yes? Okay. Using both these criteria, we compute what we call the black hole spectroscopy horizons, which is the maximum distance we average over the sky and all the angles, that a second mode can be detected using the Rayleigh criteria or the Bayes factor criteria. The first thing we can see is that the trains of the curves are very similar. So no matter which criteria you choose, you get the same train. For low mass ratio binaries, you get that the overtone is easier to detect than the higher harmonics. And for high mass ratio binaries, we get a preference for higher harmonics. In the Bayes factor, we get a better preference. But still you have the same trends between the cases. And we can see also that for the Rayleigh criteria, even the third generation detectors won't be sensitive enough to detect a second mode using the Rayleigh criteria for most of the current detector, the detection that already happened. And for the Bayes factor criteria, the third generation detectors will be good enough. I have the LISA curve here. You can see that this distance is very large, so LISA will detect almost anything. So just to check, to make this more general, we construct a signal containing all the most relevant subdominant modes and checked for we did model selection with a model containing one mode, a model containing two modes. Now we don't specify which is the second mode, and a model containing three modes. And here are the results for the black hole spectroscopy horizon. And we can see that the model contains two modes with a signal containing all the subdominant modes is compatible with the largest horizon here for the case containing just one mode. So we can shows that the analysis with just two modes is good enough. I'll just skip this, just show that we recovered the parameters of the largest horizon. And in this last plot, I'm showing the estimation of the parameters, the black hole parameters, the final spin and the final mass, using the ring down only for the detections. So when we are outside the horizon, we have the model that contain one mode or two modes to recover correctly the results, but the subdominant mode is highly uninformative. When we are on the horizon, we can see that the model that contains just one mode gives biased results, so wrong results. So we need the two modes to model correctly the signal when we are at the horizon distance. When we are at the horizon of the Rayleigh criteria, this is pretty clear that we need another mode, just get a better result with less uncertainty. I'll just stop here. Thank you.
Questions?
Very nice work and very nice presentation. Thanks.
Thank you.
I have a slightly technical question. Where do you start the ring down? How far after the
yes.
merger do you start the ring down?
We start 10 m mass after the peak. We're not starting at the peak at 10 m. The 10 m would be the time where the fundamental mode was compatible in the detection. This 3 microseconds is 10 m after the peak.
And how high in L and N can you go before where you still have something after this? I mean, there would be higher modes which die before you reach 10 m, right?
I'm sorry?
If you go to high enough L and N, which die very fast, some of them wouldn't even survive to...
Yeah, I didn't look. You mean the overtones for the L and
Yeah, the
M?
overtones and also the higher harmonics.
Yeah, the higher harmonics, the fundamental higher harmonics. Yeah, I didn't. I looked just for these 3 ones because the other ones have very low amplitude. If you look at the simulation, they are separable in the simulations. If you look at the simulations, they're not really. They have very low amplitude, so I didn't look for them.
Okay. Thanks, this is very nice.
So I have a question. So in your test where you have different modes that you add by hand, how do you adjust the different the initial amplitudes? I mean, are they chosen
Which?
from the GR simulations, or do you provide,
This?
There's a previous slide.
This?
One more.
This?
Yeah, there, where you have different modes. Right, you have
So,
these models and the signal. So the amplitudes of each of the modes, are you putting them by hand or?
Yeah, they come. I'm putting by hand because I'm doing all in the Fourier domain. So I'm not using the simulation because I would have the errors from the simulation and taking the Fourier transform of a discrete space. But the amplitudes come from the simulations at 10 m after the peak.
Okay.
So I just fit in the simulations at 10 m, then we get the amplitude.
Okay, if no more questions, let's thank Iara again.